In the last section regarding enolates, we talked about alkylation. In this section, we are going to see a different method by which a new alkyl group can be introduced at the alpha carbon. Okay, and this process will be called as malonic ester synthesis. Okay, so it is basically a method of generating carboxylic acids from alkyl using alkyl halides. Okay, so if you have an alkyl halide like Rx, you can actually convert it into a carboxylic acid. Okay, so let's see how that's done. So before that, let's look at the little bit background about the malonic ester. So it's actually a stepwise method for converting diethyl malonate, which is the compound containing ester groups, into carboxylic acid with one or two alkyl groups attached to the alpha carbon. Okay, so what is diethyl malonate? It is this compound ETO, and this is the ester group, and then again another OET. Okay, so this is diethyl malonate, and if we can use a base to deprotonate these alpha hydrogens, right, these are the acidic alpha hydrogens, then you can create an enolate here, and that enolate, at that position we can add or alkyl groups, and then finally there is a hydrolysis step which removes the one of the carboxylic acid groups, and we end in formation of a of the remaining carboxylic acid. Okay, so the first step in this malonic ester synthesis is deprotonation. So you can use, generally the base that is used, it has similar structure to this ester. So we have OET minus, okay, that the ethoxide ion would be a good base which can abstract this proton and put these electrons here, as a result of which you get this enolate. Okay, so you have this OET and then the negative charge. Okay, so first step is my deprotonation. Deprotonation. So now this is a very stable anion because it can exist in 3 different resonance structures. This is one of them. Then you can move the electrons here, put the pi electrons on the oxygen. That would create a second resonance structure, and then the third one would be where you put the electrons or put the pi electrons on the oxygen atom here, getting a negative charge on the oxygen, right? So it's kind of a stable enolate ion. The second step, so this is step number 1. Second step is the alkylation. Now you can treat this enolate that you created in the first step, okay, with a alkyl halide, and this will be an SN2 type of reaction. So I have an alkyl halide here, Rx. This can take the R group because the halogen is more electronegative, pulls the electron towards itself, as a result of which you get an alkylated compound here, where the new R group is at this position. Okay, so it's an SN2. This is an SN2 type of reaction, and second step we can call it as alkylation. Alkylation. Okay, and then finally the third step involves a decarboxylation, right? So the final step would be when this compound that is formed undergoes a decarboxylation reaction to form the carboxylic acid and generating carbon dioxide. Okay, so we can do the third step as ETO. Go ahead and draw the structure we had, or the compound we formed previously. With this one undergoes a hydrolysis reaction or a decarboxylation, okay, where it, it requires heat. Okay, it requires heat to decarboxylate, and what we end up with is a No, sorry, before that we have to do the hydrolysis. Okay, so let me put the hydrolysis. The next step is the hydrolysis, where if you recall from chapter 21, esters can be hydrolyzed to their respective acids, right? So we get an acid here. Okay, so we have a dicarboxylic acid. So we have a dicarboxylic acid, and then the last step would be where you decarboxylate by heating this, and you end up in the formation of um, the carboxylic acid and carbon dioxide. Okay, so I have this one. Oh, I'm missing a carbon atom here, so let me use that. Into my R group, and then it also generates carbon dioxide. Okay, so basically four different steps. We can call it as four different steps. One is deprotonation, alkylation, then you have the hydrolysis, and then finally it's a decarboxylation. So you can see that you started with an Rx. See, here you have an Rx, but then you ended up in formation of a carboxylic acid. So basically you can convert an Rx to a carboxylic acid by using this malonic ester synthesis. Okay? One example we can look to understand this one more time is the formation of butanoic acid. Okay, synthesis of butanoic acid from diethyl malonate. Okay, again start with diethyl malonate. It's the same compound. The starting material is the same. Okay, and the first step, remember, treat it with a ethoxide base. So OET minus. Maybe you can have sodium ethoxide, right? So to maintain the neutrality. So, and then this is step number 1. Step number 2, since we are making butanoic acid, we need CH3, CH2, Br as my alkyl group, right? So the first step creates the enolate, and then this second step will alkylate at the alpha position. Okay, so we have O, and here I have my CH2CH3. Okay, now this, if I hydrolyze it, um, I get the acid, carboxylic acid, the ethyl group here, right? And then finally the decarboxylation reaction by heating, okay, where I can eliminate a carbon dioxide molecule, and I get the butanoic acid. 1, 2, 3, 4. See, I ended up forming the butanoic acid. Okay, and then the side product is carbon dioxide, because this part undergoes a series of steps concerted, which ends up in release of this carbon dioxide. Okay, so um, I won't go into the details of how this is converted to CO2, but I think this much is enough for you to know regarding the malonic ester synthesis. So sometimes you may be asked questions by when a product might be given to you, like, and then you are asked to write down the formation of that product using the malonic ester synthesis. Okay, all right. We'll talk about aldol condensation in the next video.